So, as you can see, I just want to do a quick overview of literally our last two sessions. Today we're going to finish up the Gibbs stuff by connecting it to equilibrium. And there's just a couple different kind of problems that go along with that. You'll notice a link on my calendar here. It's also on the website, but it's the problems I'm going to use as examples, so you don't have to write them all out. You can just open it up and kind of follow along and write the work. There's one more problem set here that goes with it. And then off to the side, I've put the both Unit 4 and Unit 10 AP free response plus the past exams. Again, this isn't, if you're not taking the AP exam, you probably don't have to worry about it. If you are, it might be good to look at at least the tests and the questions just to make sure you get a sense of what's going on there. And then what I'm thinking is on our last day, the optional final will be there. It's again, it's not really much use unless you're just trying to get your grade up. I wouldn't really consider it great practice for the AP exam. It's just a short 50 multiple choice in 60-minute set of questions. So it covers pretty much the second semester, and it's a pretty uncomplicated set of questions, put it that way. So remember, the deal on that is if you beat your average in the class, whatever it may be, oh, somebody's playing music. If you beat your average, you go up by 1 grade. So that means if whatever grade you have, if you get a higher percentage on this final, your grade goes up by 1 whole letter. If you don't beat it, no harm, no foul. And so that last day you can be either taking that final during class. Meanwhile, you should be trying to make up any work you can. If again, this is just for grade repair, as it were. So that's what our last day will look at. Of course, our tearful goodbyes. And then for those of us who are going on, I'll probably have another breakout room just to kind of work with the group that's going to take the exam, so we can start planning out like, okay, what is it going to look like for our review sessions going forward after school's out? What days and times do we want to meet and such? But most of that time, other than finishing up the last few topics we haven't completed, or if some of you are still like behind in like the extra topics, you can watch those videos, or I can go through some of that stuff again. But really the main thing on the exam now is practicing the tests. So I'm going to keep kind of feeding you holistic review in the sense of full-blown AP exams for us to work through. And then again, the idea is you've developed a year-long toolbox. We've studied it in increments and in sections, but now you have to be able to go to a problem, pull out the right tool, and apply it the right way. And it's a lot harder when you're doing it with everything at once versus when you're just looking at one topic at a time. And so that's how we need to practice. Any questions so far? Okay. Before I dive into the new thing, were there any homework questions from the previous assignments that you wanted me to go over first? Anything you wanted me to look at with you? Okay. If you find anything that, if that changes, just ask, and it's okay because we're going to review a little bit now anyway. So just to kind of walk into this first, quick overview of some general things. So today's lesson is primarily on the connection between thermodynamics and equilibrium. And this connection should already kind of be implicit because when we talked about equilibrium and K, and we talked about Q versus K, we used that to predict the direction the reaction would go. Well, thermodynamics, in large part, what we've talked about has been about free energy and predicting, again, the direction of a spontaneous reaction. So there's got to be some connection between those things. We're going to find that today. But again, just to review some language issues. Remember, we prefer thermodynamically favorable to spontaneous. You can say spontaneous, but when you're making a statement on an exam, you should refer to thermodynamically favorable when delta G is negative, for example. Kinetic versus thermodynamic control, I'll wait on that because that's more important once you understand kinetics, and some of you haven't looked at that yet. So I'm not going to worry about that in the moment. But there was actually on this most recent free response that was released the other day that I showed you, actually a question that was kind of related to that. Positional probability is fancy language in reference to randomness and disorder. So like if you imagine a gas that's confined in a small space, if you open that space up and let it expand, there's a lot more positions and energies, per se, that the particles can occupy in that space. And so that represents an increase in the possibilities that exist in terms of the way the system can be arranged. And so using this term positional probability is kind of preferred language over randomness and disorder. Again, I don't think you'd be penalized for using randomness or disorder or energy or matter spreading out or things like that to describe entropy, but that's language I've seen before. So if you see it in a question, be aware that that's what they're talking about. And then the last point, the preference in making your conceptual arguments in terms of shifting reactions, unless they specifically refer to Le Chatelier, you should typically use Q versus K. And let's review that right now because it really feeds into what we're doing today anyway. So remember, when we talk about reversible processes that can achieve an equilibrium, we have said that the reaction quotient Q, and let's just take the generic reaction A goes to B, for example, right? But the reaction quotient Q is the products over the reactants. So in this case, for example, if we were working in concentrations, it would look like that. If we were working in pressures, it would look like this, same idea. And if there were coefficients, then of course they would be included here. So the idea being that it follows the same exact pattern as the equilibrium constant, but just not at equilibrium. And the most important thing about that was we were able to show that Q could either be bigger than K, it could be equal to K, or it could be less than. And the question now becomes, well, what did that all mean? Like when we said the reaction quotient Q was calculated to be larger than the value of the equilibrium constant, when you look at the form, that said that the products were too many, right? And that means this reaction would go left. Let's say, I don't want to say shifts, but reacts in reverse, I guess. Meaning, in this situation, products are turning back into reactants. When Q was equal to K, we were at equilibrium and the system was no longer changing. And if Q was less than K, we'd say, well, there's not enough reactants yet, or sorry, there's too many reactants, not enough products, I should say. And so for the ratio to be less than K, we have to, well, to get to K, we have to make more product. In other words, this is the kind that reacts in the forward direction, meaning that reactants are being converted overall into products. So that's where we last met the reaction quotient. And again, we're going to see how that plays into the way it works with equilibrium and thermodynamics. And in fact, this next equation I'm just going to drop in your lap without deriving it in any way. But I am going to unpack it. So let me recopy this on another document and really kind of label the parts, because I didn't leave myself obviously enough room. So it looks similar to, well, I guess it doesn't really look similar to anything we've seen, if I'm being honest. But let's figure out what all these parts mean. So this is still the Gibbs free energy. The difference is this is at non-standard conditions. This delta G with the little degree sign we said was the free energy at standard conditions, which we had said anything that's in solution has to stay at 1 molar, anything that's in the gas phase would be at 1 atmosphere, and the temperature would be at 298 Kelvin. Now, is there anything special about these conditions? Not exactly. But just like if you remember, maybe if you took physics, and if you didn't, that's okay. I think what I'm about to tell you will make sense. When you calculate gravitational potential energy, it's based on your height. But what is height really? Height is a reference from one point to a point above. So depending on where you set your zero, where you set your reference, your height measures a certain way. So like if you're in a room, you might call the floor the ground, and then you measure the height above the ground. But if you're in a building, you might be on the 30th floor, and you're really a lot higher off the actual ground outside. And so depending on where you pick zero, everything is just measured from there. So that's all this standard states means, is that we have to kind of pick a reference frame so that we can compare apples and apples across different reaction systems. But when it's not standard, it does change the value. Here's what's kind of cool about that, though. If we, again, think of what the reaction quotient is saying, and we just take a simple A to B reaction, and instead of putting it as Q here, for example, let's say we did it as, the actual expression. Oops. Think about what would happen if you plugged 1 molar in for everything. Wouldn't the ratio become 1? Even if it was squared or cubed, it wouldn't matter, right? The ratio would be 1. And what's the log of 1? It's 0, right? And that would make this whole term disappear. So what would happen is you would find that delta G would equal delta G naught, right? So that should happen. It should reduce to the standard value when it's at standard conditions. But what's cool about this equation is now I can push to different amounts the reactants and products and see how that affects the free energy. And ultimately that's going to connect us to equilibrium. But how? Well, here's what's really interesting to me about this equation. By the way, a quick aside about units before I get into the interesting part. Remember, the gas constant that we use has to be the 8.31 version, because that's the one that's in joules per mole Kelvin. And again, we need energy units to match energy units, which brings up another depressing fact. Since these are in kilojoules per mole, and this one's in joules, I suggest you do as we did before, put this into kilojoules when you're using it here. Otherwise, it's going to mess up your calculation. Of course, the temperature is in Kelvin. And Q, as we said, is our reaction quotient that follows the rules that we had once learned, which is, pure solids or liquids, all that sort of thing. Okay, so as I was going to say about the cool part now, at equilibrium, and this is where we're going to make the connection, two important things are true about the equation that you see up here. One, the value of the general delta G now is equal to what at equilibrium? What do you think? Anyone? What should the free energy change be once we're at equilibrium? Guess? That's not necessarily at equilibrium, but at equilibrium, think about it this way. If delta G were negative, that would imply the reaction is driven forward. It's going to proceed spontaneously forward, as written. If it were positive, the reaction would proceed backward. So how do I get a delta G where it doesn't move anywhere? 0. That's, again, that key condition that when the free energy of the system has achieved the value of 0, it has reached equilibrium. But the other important thing that's associated with that in this equation is the Q, because we've already reiterated that at equilibrium, Q is literally equal to the equilibrium constant K. Now, when we put those two pieces of information back into this equation, here's what happens. We get 0 equals the standard delta G plus RT ln times K, or just solving for delta G, we get negative RT ln K. This equation is given on the AP exam reference sheets, and it is a really cool thing because what you can do with this is now you can see it's really simple to measure for many reactions their free energies, because or really they're standard free energies, and that's how we get those values in the tables. Because you can easily figure out an equilibrium constant. You set up a reaction system, you wait till it stops changing, and then you measure the concentrations, you calculate K. Then you plug it into here, boom, you got the free energy change. Or you can go the other way. You can estimate or predict the equilibrium constant based on a calculated free energy change for a reaction. Well, the negative sign comes because if you'll notice once I put 0 in here, I have to subtract this, right? And so when I subtract this term to the other side, it's just negative that. Now, I do want you to see the equation in the other form, meaning what if I want to solve it the other way around, meaning like I want to find it in terms of K. Well, to do that, I'd have to divide the negative RT over and then take the exponential. So this is just the same equation inverted, right? Just turned around so it's solved the other way. And so we have this basic connection between equilibrium constants and free energies. So let me go back up for a moment and just, again, explain this little piece. Like, why is this little piece hanging on the edge here? This piece is basically what we can think of as a tweak that accounts for amounts other than standard. So that's how this is kind of set up. You have this standard reference free energy that is based on the conditions we defined, and then once you start moving away from those conditions, you have to add this correction to account for that extra. So that's in essence really the main idea here. Now we're just going to look at some applications and make sure you understand how to solve them, okay? So I'm going to jump now over to some problems, and again, if you want to have the problems and not have to copy down the whole question, it's the link that I put here. It's also, like I said, on my website here, but I try to make it easier by putting it right into the calendar thing. So when you open that, you're going to see a bunch of problems. Some of them are kind of older ones that I'm probably not going to do. I'll just talk through unless you want to see them. But like, this is a very straightforward, just standard free energy problem. Here's the equation. Here are the enthalpies of formation and the absolute entropies. You got to do the summation problem for this one, and then put it into that equation. In other words, you would basically have to do this little bookkeeping exercise where you would say, all right, if I need the overall delta, here it goes. I really have to figure out how that works and stop it. So here you would have to do products minus reactants, accounting for the coefficients. And then for the entropy, same idea. Sorry, I'm being a little bit sloppy here, but I think you remember these little equations. And then once I got those pieces, then I would throw them into here. And given that this is at 295 degrees Celsius, which is 298, I would just plug in the numbers and get the answer. So this is what we already did on the last assignment. So I'm not going to plug the numbers in. Let's scroll down to where it gets a little different. This just reviews the fact that if you're given free energies of formation, again, we have, for the overall reaction, a summation problem. So again, I just put that in as a reminder of another, something you already saw. Let's actually start getting to where this temperature one, we did one like this before too, where we were looking at, and just the key point here is, well, actually I'm going to solve this one because I need it for the next one. So let's go through this one. It'll just give us practice to everything I just said. So let's go through this one as kind of our starting problem. Again, we are asked to find the delta G at two different temperatures. To do that, we need the delta H, the enthalpy change, and we need the delta S, the entropy change. And then we're just going to change which temperature we're using where. So let's start by getting these changes. And I'm just going to put the results if that's okay. So under the enthalpy change, it's going to be 2 times ammonia. So negative 46.19 times 2. That's the whole side of the products, and the reactants are all zeros. So that one's done. And then for the entropy change, it's going to be 2 times the ammonia. And I'm going to turn that into kilojoules again to divide by 1,000 because otherwise I'm going to mess up, right? I have to make sure the units match. And then I have to subtract the sum of the product side. The nitrogen just once, so 191.5, and then 3 times what the hydrogen is, so 3 times 131. When I take that difference, I get negative 0.1995 kilojoules per mole Kelvin. Before we actually apply this, does it make sense conceptually that the entropy change was negative in this problem? Here's the reaction. Why does it make sense that the entropy change is negative here? Based on just conceptual arguments. Anyone? Look at the equation. We did the math. More moles to less moles, good, because there's less moles of product and everything's in the same state anyway, so it's just fewer moles is the key argument. But I just thought it was nice to make that connection. Now, at 25 degrees Celsius, the free energy change, if we use these numbers, and just for the simplicity, I'm going to leave the units out at this moment. 298 times negative 0.1995. So when I do the 25 degrees Celsius problem, minus negative, I get about negative 32.9. So that's at 25 degrees Celsius or 298 Kelvin. Now before we do the math, can you tell me or predict whether you expect the delta G, the enthalpy change, to be greater than, less than, or equal to this one when we raise the temperature up to 500? So don't calculate it yet, but see if you can predict it. Think about the signages and the favorabilities. Will raising the temperature make delta G more negative and therefore more spontaneous or less? So somebody's saying greater. Any contradiction there, or anyone want to discuss that? Higher temperature is better here, you think, to drive it forward? Well, let's try it and see, since you're all so quiet. All right, so we're just going to do the same calculation, but at 773 Kelvin, right? Times negative. And let's see what that gives. Wait, that's the wrong number there, sorry. I copied from the wrong place. It should be negative 92 point. My bad. All right, let's do that again. Negative 92. Negative 92.38 minus 773 times negative 0.1. Whoa. I got like 61.8 positive. What is going on here? Let's interpret what this is saying. So I have to understand, when you said, Sophia, that it would be greater, did you mean like greater, more positive, like we're seeing here? Did you mean greater, like more negative and more spontaneous? Let's unpack this. Okay, so more positive, the way you said it, is correct. Now let's think about what this is saying. First of all, if we go back to the original data here, the enthalpy change being negative and being exothermic was a thermodynamically favorable change promoting spontaneity in the direction indicated. But the negative entropy goes the wrong way and makes it thermodynamically unfavorable. And we said that as the temperature gets higher, it amplifies the entropy effect. So if the entropy is against me, as T goes up, delta G becomes more positive, which is a bad thing in the sense of thermodynamic favorability. In fact, we went from something that was pretty thermodynamically favorable to this high temperature where it's thermodynamically unfavorable. And in fact, look at the logic of this in the context of what we see. For this forward reaction, elements are combining to form a compound. They're coming together. At the lower temperature, that's favored. But at this temperature, the higher energy of the particles as they're bouncing around is causing it more likely to go the other way, for the compound to break down. So you see here the thermodynamics flips because of the temperature change. And so depending on what you're trying to do here, if you want to make ammonia, it's better to be at a lower temperature. Now what's actually interesting about that is, again, this doesn't tell me anything about the speed of the reaction. This is one of the industrially most important reactions in the world. This is the basis of what's called the Haber process. At one time it was used, or initially used for warfare. They were trying to extract nitrogen from the atmosphere to use it. This is during World War I. And they were doing it to make nitrates ultimately from ammonia so they could make explosives and gunpowder. The original source was bat guano, which was mined off of caves on the coast of Chile and somewhere around South America there. But the blockades of the Allies stopped this shipment, and the what were they called? The Central Powers, I think, in World War I. The Central Powers didn't have a source of nitrates to make their munitions, and so their chemists came up with this process on, in an industrial scale. And this prolonged the war, possibly for years, because they were able to produce right out of the air with some other components, of course, because the nitrogen is plenty in the air. They were able to produce this. And so it's like, wow, what a bad bunch of chemists. They're killing people. Well, ironically, that same process now consumes somewhere up around 1 to 2% of our entire energy output in the world. And it's used not for munitions primarily, but now for fertilizer. So this reaction, which first maybe caused the deaths of thousands or maybe even millions, fed billions, and has since, because it's completely revolutionized food production in terms of making land more productive, because now you don't just collect animal waste for fertilizer, you can produce it en masse and really make fields more productive. Anyway, interesting little bit of history there, but the thermodynamics and the kinetics play a role here, because thermodynamics says this works best at low temperatures. But low temperatures make reactions go slower. And so you have to balance those effects, and then you have to find ways to speed up the reaction that do not require a really high temperature, like using catalysts or the conditions of pressure and volume and all that stuff that you can play into it. So again, a lot goes into these kind of things, but I just think it's cool that our little problem illustrates that. Now, let's take this to where the equilibrium piece comes in, and how the drive is affected by changing the conditions. So take a look at this reaction here. It's the same reaction. We're at the same temperature, but now we're asked to find delta G, the free energy change, at these non-standard conditions. So I'm going to write this equation again. And let me write it twice. I'm going to write it a second way by just substituting one thing. And I hope this makes sense when I do it. So instead of Q, I'm going to write Q in the form that it should be symbolically. And since they're giving me all the amounts and pressure units, that's what I'm going to work with. So product is ammonia, so its pressure would be squared. And the reactants are nitrogen, and that would be to the first power, times hydrogen pressure cubed. Now, if we take the value for delta G at 298 we got on the last problem, because that's what we need that standard value of negative 32.9, we can plug that number in. Well, it's too fast. So let me do that. Our gas constant, we said, has to be the 0.00831. That's in kilojoules per mole Kelvin. Our temperature is still 298 because that's where we're staying with this one. All we're changing is the mix. And again, our Q is based on the values that we're given. So in this case, let's see, our product was ammonia. That's given to us at 0.5 atmospheres, and that gets squared. Our nitrogen is to the first power and is 1. And then our hydrogen, oops, that's cubed. So we're just plugging in these values. Let's calculate a number and see what we get and see if it makes sense conceptually. I always like to do that. It's not just a number. It's does the number actually have meaning in a way that I can understand why the number went that way. 298 times ln of the quantity squared. I get a negative 44.5 or so. Now what does that tell us about these conditions compared to the standard conditions? Here's the conditions that we get, or here's the delta G we get at these new conditions. Does this imply anything about compared to standard conditions? Meaning the fact that it's more negative tells us what? Oh, that's cool. I just noticed in the chat that reference to the book from Sophia. Thank you. I want to check that out. So what's the implication here, folks? Like the fact that it's a bigger negative number tells me what about these conditions compared to standard conditions? And I guess let me give you like a multiple choice question here. Does it mean the reaction is more driven forward, less driven forward, driven backwards, not changed at all? What is this telling me? What do you think? Remember, if delta G is 0, we're not going anywhere. If delta G is positive, we're going backwards if we can. And if delta G is negative, we're going forwards as written. So it's definitely going forwards. And I see Miriam saying it's more thermodynamically favorable, and I agree with that. So two things we can interpret is it's more driven in the forward direction. Furthermore, it also means we can extract more work out of this system, right? So if we look at how the reaction started and how it ended, I think this makes sense. Let's see if I'm right. So it's standard conditions, everything was at 1 molar. I'm sorry, 1 atmosphere. And that's when we calculated a value of negative 32.9 for this delta G. Notice that when we changed conditions, we kept the nitrogen at 1, but we pumped up the amount of hydrogen and decreased the amount of ammonia. And if you just think about that conceptually, we've pumped in more reactant and pulled out some of the product. And so in general, that seems to suggest we're driven even more this way. Because if you think about it, just even from a Le Chatelier point of view, increasing reactants and decreasing products should shift us more to the right. So all of these things are consistent. They all connect to each other, and they all tell us a piece of the same story in a different angle. Any questions about that so far? Okay. I'm not going to go through all this here because, again, it's a lot more of the same stuff. I'm going to skip ahead to where the numbers are already kind of figured, and we're just going to show how to get K or delta G from one or the other. So let me jump ahead a little bit here, like this problem. Consider the following reaction at 800 Kelvin. An equilibrium mixture, key word there, contains the following partial pressures. And then it says, well, what's delta G for the reaction? Oh, delta G standard. Let's make sure we realize that. Well, in this case, there's really no reason for us to calculate this. So we're not even starting here because we're told it's already at equilibrium. Therefore, we're really starting here. The problem is we need a value for K. The good news is we have all the information to find it. Because in this case, it would be the pressure of the product squared over the nitrogen times the pressure of the fluorine cubed. And again, if these were concentrations, it would follow the same pattern. So we just have to find K first. 0.48 squared over 0.021. And then what's that? 0.063 cubed. So let me get that number. Third. I get like, I'm just going to round it, 4.4 times 10 to the fourth. That's a pretty big value for K, isn't it? Like 44,000. This really favors the products. Now, if we just plug it in here, we can get a delta G and see again if it makes some kind of conceptual sense. Watching my units again to be in kilojoules. Our temperature, since we are at 800 Kelvin, that's what we put in. And then the natural log of the number we just got. Sorry, it's getting smushed. So negative 0.00831 times 800 times ln 4.4 E4. I get syntax error. Of course I do. Oh, I forgot the E. 4.4 E4. There we are. So I get like negative 71 kilojoules per mole. Now let's think about what that means. Delta G had a rather large negative value, which means it's very thermodynamically favorable that this system can give us work that we can extract from this reaction. But notice that's also that K is very large. Is that connection consistent? Is that always going to be true? Or is it a coincidence? Let's take a look. So watch this now, because I think this really hammers home this point nicely. And to make this clear, I'm going to put the exponential form back up for a moment. We know that R is a positive number. We know that T in Kelvin is always a positive number. But delta G can be positive or negative, right? And this negative sign is actually part of the equation. So take a look at this little table, and it shows you the direct connection between the free energy change, meaning the standard free energy change, and the equilibrium constant. When it's positive and large, K is really small. As delta G approaches 0, K approaches 1. As delta G becomes negative and larger, K gets bigger. Look at the logic of this two different ways. If you put a negative value in for delta G, the negatives cancel and you get a positive exponent. You're going to get a number greater than 1. If you put a positive value in for delta G, you're going to get a negative exponent. And therefore you're going to get a number less than 1. Conceptually, both of these are saying different ways what we expect the system to do as it approaches and reaches equilibrium. The larger the positive value, the smaller the K is for the forward direction, and that's why we stay essentially all reactants. When K is somewhere around 1, we're going to get a mixture of reactants and products, a significant amount of both. But as delta G becomes negative and more negative and more negative, we're saying the forward direction is being driven more and more, which is the same thing as saying K is very large. which is the same thing as saying we're going to end up with a lot of product and not much reactant after we reach equilibrium. So hopefully you see that these are consistent and how these are connected. Any questions about that? Okay. Let's just look at a little bit more calculation, just so we can make sure you know how to, let me see which one I want to do. No, that's the same stuff. Not that one either. I just want to make sure you can go backwards and forwards, meaning that you can, if you're given the equilibrium, no, let's do it like this actually. I'm just going to go back and pluck one out just for the sake of argument. Let's just do a math problem. So let's say you're given that delta G, oh, actually we had it earlier, for the ammonia problem, was what, negative 32.9, I think? Could we find the equilibrium constant for that reaction? And of course it's at the same temperature. So that was when we had calculated it at 298 Kelvin. Again, this isn't hard, it's just do you put the numbers in correctly. So let me actually bring my calculator forward and let you see what it should look like. Oops. Again, it's just a question of being careful with your units and your signs, really. But to find the equilibrium constant in this case, you would have to take the exponential of negative delta G, because again, we have the negative sign that's in the equation versus the negative value of delta G. The R is the 0.00831, and that's an, oops, per mole Kelvin. And then our temperature in this case is 298, as we said. Sorry, it's getting smushed in there. All the units have to cancel out because you can't raise something to a unit power, right? You can't raise something to the 3 eggs. It doesn't make any sense. So just to see how that types in, oh, of course, yeah, Miriam, you could just find the exponent first, and then you do E, remember the exponential function E. So I'm just going to type it all in at once, but it's the inverse natural log there, and you see it sets it up for me. And then I already see the negatives cancel, so I'm just going to type in 32.9 and divide that by the quantity of 0.00831 times 298. And then I'll close that parenthesis and then the outer parenthesis, and bam. In this case, I got about 5.9 times 10 to the, about 10 to the 5th. Okay, my little writing pad is deciding to go mad. But anyway, that should show you, really, I guess it just wants to be there, that line. But that should basically show you, again, that when you have a very negative delta G, that's consistent with having a very large equilibrium constant. And hopefully that's not that hard to do. It's just a matter of understanding. Careful with the sign, careful with the units. Main point. Now, really there's only one last thing to tell you, and then I'm done. Ergo, when you're done. So we talked briefly about coupling last time. Let me just jump ahead and let's start with this one here. So this shows that the decomposition of calcium carbonate into calcium oxide and carbon dioxide is very thermodynamically unfavorable at standard conditions. This is saying show that combustion of carbon, like in the form of, let's say, coal or something, can be used to drive this decomposition. It's just Hess's law with free energies. And it's really, really simple, because when you think about what this is saying, is if I added the two equations, what would happen is then I'd add the two energies. And here I didn't do any flipping around, any dividing or multiplying. So I literally just add the two numbers, and I get, in this case, What do I get in this case? Whoops, sorry. I hit the wrong button. Ugh. You know, the calculator should do as I say, not as I do. Why can't it read my mind? Alexa! Just kidding. Um, so now the process, the combined process, is quite thermodynamically favorable. And so here's what we're saying. And this will make perfect sense when I describe what this is really talking about. Right? On the paper here, it's like, okay, we're doing this, and this, and this, and we're getting calcium oxide and 2 carbon dioxide units. But what we're saying is simply this. If you take calcium carbonate, which is a component in things like marble, limestone, and you set it on the table, it sits there forever. Like nothing, but it just doesn't decompose. It just sits there at room temperature, which is good because if you have like marble sink tops, you won't want them decomposing in your kitchen. However, if you take some coal and burn it, the energy, the free energy released by that process can be used to drive the decomposition of calcium carbonate. So again, think about all the things in the world that we use energy to do. And this is essentially what coupling means. You take something that on its own is non-spontaneous and you drive it with payment from energy released by a spontaneous process. So like your cell phone, take out the battery, nothing happens. It does not spontaneously light up and play your games or make your calls or text your friends. Put in the battery, there's a reaction in the battery that couples, so to speak, with what the phone wants to do. And so the free energy released by the chemistry in the battery now is used to drive the phone. And again, this is the whole idea that we started this whole unit out with, that things like us can exist, can be alive, can be this, what appears to be flouting the laws of thermodynamics by creating order out of chaos rather than the other way, by concentrating energy into these units that we are, these cells and these bodies and these thinking creatures, because we pay for it at the expense of coupling it with other free energy sources like the sun itself, driving a lot of the processes on Earth and the chemistry we do in our bodies. But again, it's a limited supply. Free energy is only so much, and once it's all used up, poof, bye-bye. Sad. Okay, so that's kind of it. The last problem set is about this, and then, like I said, for those of you who will take the AP exam at our next meeting, we'll figure out how that's going to look. So today at 2 o'clock, I will do and record the next piece of electrochemistry stuff. I will see you there, hopefully. Have a lovely weekend. You're free to go. Oops, I'm going to stop that.